Now I will do a introduction about AC-DC power supply. AC-DC power supply is like a system that changes the AC input to DC output. This to ensure the compatibility and reliability for a wide range of electronic applications. First, we have to know what is AC-DC. Direct currents, where the direct current DC is a current that only go to one directions. So for AC, the current have two directions, forward and reverse. So we can observe the shadow graph. So this is a block diagram. This is the AC input and this is DC output. So AC input, after going through few process, if we go to this shell, if we go to DC output, so we then go to few block, transformer, rectifier, smoothing, and regulator. Now we go to first block, is transformer. Transformer can tell us to reduce the voltage because if you take the input and change to different output, diodes, they only allow one current going to one range. So the original AC signal is like this. After doing rectification and rectifier, we get this type of graph. So diode can operate in two conditions. First is forward bias and another one is reverse bias. So when forward bias, diode can allow current pass through it, but reverse bias current cannot let the current pass through it. So as smoothing process, capacitor is an electrical device that store electric charge. So at this point, capacitor charging and the voltage want to drop, capacitor will release the charge, try to maintain the voltage. So the graph in bottom here is this. So this is a graph without capacitor or without filter, but with filter or capacitor. So if you try how to maintain the ripple or reduce the ripple, this is Zener diode, either last voltage regulator part. Zener diode is designed to operate in reverse breakdown. So when the voltage across Zener is higher than the Zener voltage, if you try to start operate and clamping the voltage, so you like reduce the over voltage to the voltage limit is set. So now it's a part of circuit analysis. We can know that the formula we use is Vs over Vp equal to square root Ls over Lp. So Vs equal to 2 over 800. 2 is Ls, 800 is Lp, which is primary, and square root. And we multiply with 240 because this is the power supply. So this, we can get V secondary is 12 watt. So this is step down transformer. And the voltage we get, and we then send to rectifier to do rectifications.
After we getting the V secondary peak, we can move to the mover rectifier bridge. This one is a rectification of the AC power supply to convert our AC to DC Austin DC. And then for the rectification bridge, it could include with the four silicon diode with the knee voltage VT equals to 0.7 volt. So in the positive half cycle, we can see from the graph. From the graph, we move through the D3 with the 4 bias, and then it moves to the V secondary peak. So it is 0.7 minus with the 12 volt, and then it pass again for the D2, and D2 is another one for the 4 bias. So we can get the V secondary peak by using this KVL, and the value will be the 10.6 volt. After that, we do the same thing for the negative half cycle. For the ground, we move through the D1. D1 will be the 4 bias, and it's the turn on, and then it minus with the 12 volt, plus again with the D4. D4 is further another silicon diode, which is a 4 bias and turn on. And we will get the same value for the VP out, which is also 10.6 volt. Then we move through the capacitor. By using the formula of V equal peak to peak, the V equal peak to peak is a peak to peak voltage from the highest peak and the lowest peak. So we can know that the highest peak is the 10.6 volt and the lowest peak is another one for the value right here. So initially we don't know. We use the formula VP out equals to 2FRLC, and we substituting all the values inside, and we can get a 1.06 volt. So we can know that when 10.6 minus with the 1.06 volt, we can get 9.54 volt. And that one will be our VP minimum. Then after its filtering, it will move through the Zener diode. The Zener diode as a voltage regulator, it will only be operating in the reverse region, or we can say that it's a voltage breakdown region for the Zener diode. So when the Zener diode is turned on, it will give the send output voltage as this will be VZ. So we can know that VZ, which we set it up as F12, and output voltage is F12 also because our Zener diode is turned on. It will regulate the AC power supply, maintain at the same strength like DC. So for the AC, we know that our voltage is varies changing from the minimum to the maximum. And just now we calculated 9.54 volt and the 10.6. So our 9.54 will be the minimum voltage and the 10.6 will be the maximum voltage. Another one for the RL. RL will be the constant variable, and that one will be the constant for our calculation after this. And the variable is a Vs and also the Zener diode. In order to determine the current for the Zener diode, there is a formula also for the Kirchhoff's first law, which is a current law. The total current entering a node is also the total current leaving a node. So we can know that the IS entering and IZ and IL is leaving. So IS, when IS is maximum, the E equals to IZ maximum plus IL minimum. And when we are determining the IS maximum, it will be the KVL again by using the maximum voltage of the value we get, 10.6 minus with the F12 over 100, and it equals to IZ maximum plus F12 over 1000. So you can get the IZ maximum is roughly equals to 15 milliampere. And we will do the same thing for the IS minimum. So we know that IZ minimum is equal to 8.2 milliampere hour.
So I will continue with the LT-SPICE simulation part. So let's look at the transformer first. So in LT-SPICE, we don't have the transformer as usual we have. So we need to build out a transformer using two inductors. So with the formula of transformer, which is Vs over Vp equal to square root Ls over Lp. So we can build out a transformer by using two inductors. So right here is 800 to 2, which is also a 4 to 1 transformer. So let's observe the simulation waveform. So let's check the primary voltage first. So for the primary voltage is 240 watt alternating current. So for the secondary, you can see that the voltage is about 11 to 12. Now, after the voltage pass through the transformer, they will enter a rectifier that built up by 4 diode, which can produce a pulsating DC voltage. So before we insert a capacitor in here, we can simulate the LT-SPICE first. So let's check the waveform after the voltage pass through the rectifier. We can see that this is a clearly pulsating DC voltage, which is all the voltage is positive. So there's no negative voltage right here. If we insert a capacitor here, and we check the simulation waveform again from after the capacitor, and which is a voltage waveform that is already filtered by the capacitor. So which is much smoother and more close to the straight line. So after the capacitor, we simulate again, and we check the voltage after the Zener diode, which is the voltage at the resistor root. We can see that the voltage is in about 8.2 DC voltage. The voltage is 8.2 because the Zener diode we use is a Zener diode with a voltage breakdown at 8.2 watt, and the module is this one.